Let's take a look now at section 15.7, and let's talk about the divergence theorem. This theorem, also sometimes called Gauss's theorem, states the following. Let's start off with a solid region Q. All right, now that's a solid region, not just the surface, but the actual stuff inside. So physically, you would have maybe a sphere, or something like that. Yeah, all the stuff inside. All right, now let's say that surface is bounded by let's say that region is bounded by a closed surface. So here Q is the sphere, whereas S is the outer surface of the sphere. Okay, so Q is solid, including all the stuff inside. S is just the outer layer. Okay, so let Q be a solid region bounded by a closed surface S that is oriented by a unit normal vector oriented outwards from Q. That is to say that the unit normal vector is going outwards from here. So here you would have it going in opposite directions. Here, this would be flowing this way. Here, it would be flowing this way. Right? And of course, at every point, it would be flowing in its own respective direction, but it would always be flowing outwards. Okay, so your unit normal vectors are outwards. Okay, now let's consider a vector field, f of x comma y comma z. Let's let that be a vector field whose components have a continuous first partial derivative within this region of Q. Assuming we have all of those conditions met, then the flux integral of f through s is actually given by the triple integral over the region Q of the divergence of f with respect to volume. That is to say, the surface integral, the stuff on the outer edge, can be given by the triple integral of the stuff inside of this outer skin. This is a generalization of Green's theorem. You'll remember Green's theorem told us that if we were looking at what was going on around the outside of a region, the outer edge of a region R, and a contour C that was oriented this way, what was going on the outer edge could be given as long as we knew what was going on the inside of that region. All right? So Green's theorem tells you how you can use a curve to give you the double integral, or vice versa, the double integral to give you the contour integral. Here, this is moving up a dimension. It's telling you how you can use a triple integral over a solid region to evaluate a surface integral. All right. The proof of this one is a bit more advanced than what we're ready to do in this course. Anyone who goes on to higher level analysis will see a proof of the divergence theorem. Any proof of the divergence theorem which we could see at this level would be very incomplete. At best, we could here I could prove it for this sphere, because the sphere is nice and simple, but anything more complicated than something like this, it's just not accessible to us. And so instead of proving a very childish version of it, I'm just going to say the proof is omitted, or maybe let's say proof is left for later courses. How about that? I'm going to assume everyone here is going to take senior level analysis eventually, because sure, why not, right? Left for later courses. And now, even though we are not going to prove this, we can still at least talk about why this should be true. We can give a little intuition, talk about what this means. All right. Imagine you have a solid region. All right. So inside of here, you have every point is included. All right. Now, that solid region Q is bounded by some skin, some surface, which we call S. All right, now, I have a vector field which is flowing through. I have vectors which represent the flow of some fluid. Now, of course, it doesn't have to represent that, but for the purposes of this explanation, it will. Now, what I want to know is, what is the flow through this skin? All right, that's what a flux integral is. A flux integral is, okay, I've given you a surface, I've given you a vector field, which, again, for our explanation, you can figure this as here's some flowing fluids, a gas or a liquid, and here's a direction. And how much of that fluid is flowing in that direction through that surface? Okay, so here what I want to do is I want to figure out what's happening here and what's happening here. Okay, well, notice that one way I could do it is I could talk about what happens here and then separately talk about what happens here. But another way I could do that is to look at what happens inside. Consider a small little cube in here. Notice that the flux, the flow rate going in is roughly the same as the flow rate coming out. Because this is a tiny little cube, the flow rate doesn't have much of a chance to change. That's why we need this vector field to have components that have continuous first partial derivatives. If the first partial derivatives are continuous, then the function is also continuous, and you don't have massive changes over small distances. So here, whatever happens to the flow rate going in is roughly the same thing as the flow rate coming out. You say, okay, so what? Well, I could keep doing that. I could break this into a bunch of tiny little subsequent and connected little boxes. And I note that whatever is the flow rate going into one of these boxes is going to be roughly the same as the flow rate coming out of one of these boxes, all the way from the beginning until the end. All right? So what this is saying is, okay, I have this vector coming into my box. Okay, now I have this vector coming out of this box, but then going into the next one. So notice if I'm orienting in a particular direction, this is like saying it's a positive, whereas this is a negative. This is coming out of a box versus going into a box. Notice we have the vector oriented outwards, normal vector oriented outwards. So anytime something comes out of a solid, we're considering that a positive direction, a positive integral. And anytime it's going into an object in the opposite direction, you consider that a negative. So here, if that flux at that point is positive 1, then into the next box, since it's right next to it, that would be negative 1. And same thing here. If that flux coming out is positive 7, the flux coming in is negative 7. And notice that as I measure the flux coming out of one of these cubes, it's immediately canceled by the flux going into the next cube. So by the time we get to the end, every one of these flux that we've measured is canceled out by the previous one. Oh, well, except for this one, because it doesn't have a previous one, right? This is the first one that came in. And then up here, I have another one, which isn't canceled by anything because it doesn't have anything to cancel with, right? This one cancels with this one coming in, but now this one coming out would cancel with the next box that I'm going into, but there is no next box. So here there's nothing before it to cancel with, and here there's nothing after it to cancel with. So if I consider every one of these vectors, every flux integral through these boxes goes away except for this very first one and this very last one. So now imagine I do that for every possible path through my sphere. Well, then I'm going to have all of these cancel out, and the only ones that are going to remain at the end are the ones that are affecting the surface of my sphere. But that's exactly what I want. I want to figure out what's happening at the surface, and I can do that by considering the objects on the inside. But now the question remains, what is that thing? Okay, here this is here's a vector field, here's a direction, and here's a surface. And this statement essentially says, here's how much flow there is in that direction through that surface. Okay, this says, okay, I have a triple integral over volume. I'm adding up a bunch of things that happen at each of these little pieces of volume, at each of these little cubes. But what is it that I'm adding? What is the divergence of F? Well, we know the divergence of F. It's just the gradient, it's the differential operator del dot F. Oh yeah, that's the notation. But what is it? Oh, well, it's the partial with respect to x of the first component of F, comma, the partial with respect to the plus the partial with respect to the second derivative of f, plus the partial with respect to the third derivative of f. Okay, well, that's how we compute it. But what is it? Like, what is this thing? What is it that we're computing? Well, in order to see that, we can take a look at this definition, or rather this theorem, and use that to help us define contextually what the divergence of f actually means from a physical standpoint. So notice, this is your flux, right? So that's going to be flux. And that's the flux of f across this object. All right, now to help us see this a little bit better, assume this object is extremely tiny. All right, so here, or in fact, let's just assume that we're looking at a little tiny piece of this object, maybe just to keep that in context. Assume that you have a little tiny sphere within the big sphere, okay? Now, so let's call this surface, let's just call this one S epsilon, right? A little tiny surface of radius epsilon. Okay, well, the flux of F across S sub epsilon would be given by, well, this thing right here, right? That would be the double integral over S epsilon of F dot N ds, and that's given by the triple integral Q of the divergence of F dV, like that. All right, so here I've just rewritten the results of my theorem. But now notice that because this is a really tiny little thing, then Q, the space inside of this, in fact, let's call that Q epsilon. Notice that that Q epsilon, the solid inside of that surface, is also very, very tiny. So here, this could be approximated by a little tiny cube. So here we could say, okay, well, let's say I have a little bit of volume, all right, so that's approximately delta V, a little tiny cube inside of there, times, well, the divergence of F. All right, so here the flux of F across this little tiny surface is given by the triple integral over the stuff inside the surface, inside the sphere, of the divergence of F dV. But again, because this is a very, very tiny little bit of volume, we could approximate this as just the divergence of F times that little tiny volume. But now, if I want to figure out what this divergence means, well, notice it's practically by itself already. I just need to divide this out over this way. Here, let me say volume epsilon. I'm just using epsilon to denote that it's a very tiny little piece in there. Okay, so now if I divide both sides by this, I get that let me write it up this way, I get that the divergence of F is equal to the surface integral over S epsilon of F dot N ds over delta V epsilon. Or in other words, I get, well, I guess this should be approximately equals to. I get that the divergence is approximately equal to, well, that's just the flux across that surface. It's flux across S sub epsilon divided by the volume inside of F sub epsilon. That's the physical interpretation of divergence. It's flux per volume. Since flux can be thought of as a flow rate, you can think of this as flow rate per volume. How big is this? Okay, now, how much flow is there per unit of volume? That's what we physically can interpret our divergence as. Whenever we talk about the divergence with a physical interpretation, there are three possibilities. We saw when we first defined divergence that there was a name for a vector field whose divergence is 0, and that was an incompressible vector field. It turns out that we have names for more than just that. Note, this is more physical interpretation if you take physics or thermodynamics or anything like that. Oh, incidentally, in thermodynamics, you'll see flow rates not of fluids or gases or things like that, but you'll see flow rates of heat, the heat equations, as they're called. So in any event, if you have a vector field let F be a vector field if the divergence of F, often denoted as del dot F, is equal to 0, then F is said to be incompressible. Incompressible. If the divergence of F, again denoted del dot F, is greater than 0, then your vector field is called a source. Although, I think my notation here might be a little misleading. It makes it seem like I want the divergence of the entire vector field. Here, let me denote it this way. Let F be a vector field, and let's say x naught comma y naught comma z naught be a point in the vector field. So I mean, you can have sources and you can have points that are incompressible. It doesn't apply to the entire vector field. It applies to specific points. So here, let me write this a little more with a little more detail here. My apologies. This does seem a bit misleading here. So I'll just write it this way. If the divergence of F at that point is equal to 0, then that point, then F at that point is considered incompressible. Right? Incompressible at x naught comma y naught comma z naught. If the divergence of x naught comma y naught comma z naught is greater than 0, then F is a source. Maybe we should say has a source. Has a source at x naught comma y naught comma z naught. There we go. And if the divergence of F at x naught comma y naught comma z naught is less than 0, then F has a sink at that point, x naught comma y naught comma z naught. Like that. Visually, what that looks like is if you have a point in your vector field, imagine you have a little tiny sphere around that point. If the divergence at that point is greater than 0, then that means that from that point outwards, your vector field is flowing only outwards away from that point. So in your vector field, it looks like your vectors are coming from that point. They're all moving away from there, so it looks like this is their source, hence the name source. If you have a point and you imagine a little sphere around that, and you imagine, oh, now every one of my vectors is coming toward my point from every possible direction, that's called a sink. All right. Note that it does, here's the exaggerated view. It is possible to have a vector field that where most of these are coming out and you might have one coming in or two coming in. Here, this is more of a net effect. The net effect is things are moving away from the point. Here, the net effect is things are moving toward the point. And it's incompressible if you have where you have equal amounts of stuff flowing out as you have coming in. Like that. Okay. And again, these are overly simplified drawings, but the computations would tell you exactly what's going on. If you have a vector field and you have a point over which your vector field has been defined, then the divergence of F at that point is equal to 0, greater than 0, or less than 0, tells you that that point is either a source. The net effect is that vectors are coming from that point. It's a sink. The net effect is vectors are going to that point. Or incompressible, the net effect is that, well, you don't really have either. It's a balance between the two. Let's see here. It looks like, there we go. I went slightly out of focus. That looks a little better. Let's see, maybe a little more. No, that's too much. There we go. That looks about right. Okay. So that's some language that you'll run into if you take university physics, or if you take thermodynamics or anything else. You'll run into this kind of language. So now let's take a look at some examples of how to use the divergence theorem, how to use Gauss's theorem to compute a flux integral. Now remember, there is one consideration, an important consideration. To use the divergence theorem, to use Gauss's theorem, your surface must be closed. If it's open, if it's just the upper hemisphere, or if it's a plane or something like that, then you have to do what we did in the previous section, and that's just compute the flux integral from its definition. But if you do have a closed surface, a sphere, a paraboloid closed off by a plane or whatever, as long as it's completely closed, then the divergence theorem, Gauss's theorem, is a very nice short way to compute that flux integral. So let's take, for example, that we want to find the flux integral f dot n ds, given that we have a vector field f of three variables, x, y, and z, that is given by the vector 0, comma, x, y, z, comma, 0. Okay? We're given a surface S that is bound by, it's a surface that bounds a region, and it's made up of three individual surfaces. It's made up of x squared plus y squared equals to 4. Notice you're missing one variable, which means it's a cylinder. And here we have two other boundaries, z equals to 0. That's a plane. That's parallel to the xy plane. In fact, it is the xy plane. And here we have another plane, z is equal to 5. And that's also parallel to the xy plane. So as a quick visual, notice that that's a circle of radius 2. Oh, but it's a surface in R3. Oh, okay, so then it's the cylinder whose generating curve is the circle of radius 2. Something like that. Here, this is going to go up and down forever, but we're going to bound it. We're going to bound it below by z is equal to 0, which is the xy plane, and we're going to bound it above by z is equal to 5. So here we want a cylinder, but we want it to start at the xy plane, and we want it to go up to a height of 5. So this is our surface over which we're going to find our flux integral. Okay, so by the divergence theorem, here notice that this is a solid region, right, inside. It's bound by all sides, above and below. So it does match the requirements needed for the divergence theorem, namely that you have a solid region that is completely surrounded by a surface, or in this case, a collection of surfaces. I guess I should write here. So the question is, find the outward flux. Because remember, our orientation for the use of the divergence field should be outwards. If it were inwards, of course, it would just be the opposite. But here, to use exactly the divergence theorem, it should be an outward flux. Okay, so here that's going to be given by our theorem. Namely, it's the triple integral over Q of the divergence of f dv. Now remember how the divergence works. The divergence is given by the first component. We're going to take its derivative with respect to the first variable, namely with respect to x, plus del n del y plus del p del z dv, like that. So here we can go ahead and find that. The derivative with respect to x of the first variable, well, that's just 0. The derivative with respect to y of the second variable, well, that's xz. And the derivative with respect to z of the third variable, well, that's 0 again, over the volume of Q, which of course is just the triple integral over Q of xz dv. Now, I notice that I'm going to take a triple integral over the volume of a cylinder. Well, then use cylindrical coordinates, right? Just the name of it implies that's what we want to do. Could you do it using rectangular coordinates? Absolutely, you can. It is doable. You can bound all these things using rectangular coordinates, but note that the boundary here would be your x value would be bound by the positive and negative square roots of 4 minus y squared. And that just sounds like an unpleasant thing to have to integrate with respect to. So here, cylindrical coordinates are probably the way we want to go. You don't have to, but I figure it's probably for the best. So here, let's go ahead and take the triple integral. All right, let's write that as the triply iterated integral with respect to polar coordinates. All right, so here we're going to write this as now, since we're changing to cylindrical coordinates, dv is written as r dr d theta dz. X is going to be written as r cosine of theta, and z just stays z in polar coordinates. Right? So here, that's your x, that's your z, and all of this stuff right here is your dv. That one becomes that. This one stays as it is, and this one is that one there. But now that we're describing things in polar coordinates, this is simple enough to do. Right? Notice that the base of this cylinder is just the circle of or either, I guess I should say the disk, because it doesn't occupy the stuff inside. It's the disk of radius 2, which means that the radius is going to go from 0 to 2. It does go all the way around. I don't just take a portion of this disk. I take the full disk all the way around. So theta will be from 0 to 2 pi. And z, well, that's given to us from 0 up to 5. So here we have our boundaries from 0 up to 5. So here that's going to be the integral from 0 to 5, of the integral from 0 to 2 pi, of the integral from 0 to 2, of r times z times cosine of theta times another r. Oh, okay, so we can write that as r squared z cosine of theta dr d theta dz. Right? So there's our setup. Notice we don't have to worry about our 3 separate boundaries. We don't have to worry about finding the outward flux integral for all 3 of them. Note that if we were doing that, we would have to find 3 different integrals, since the outward flux integral here would be going up. The outward flux integral here would be going down, coming out from inside of this region. And notice that the outward flux for this one would have to be oriented horizontally. We don't have to worry about any of those things. The divergence theorem allows us to take all of this as a single triple integral, which Fubini's theorem allows us to take as a triply iterated integral. So now it's just a matter of integration. This is going to equal to the integral from 0 to 5 of the integral from 0 to 2 pi of, with respect to r, this is going to be r to the third over 3 z cosine of theta, evaluated from where r is equal to 0 up to where r is equal to 2, d theta dz. Okay. That's going to be, well, let's see, if I plug in r is equal to 0, the whole thing's 0, so I don't care about that. But if I plug in r is equal to 2, 2 to the third is 8 over 3. And that's a constant, so I can bring that out. So this would be 8 over 3 times the integral from 0 to 5 of the integral from 0 to 2 pi of z cosine of theta d theta dz. Right. That is a constant now. That came out. And now I still have 2 integrals to take, z cosine of theta with respect to theta, then z. Okay. If I take the integral with respect to theta of this, well, that's just going to be a constant. So that's going to be 8 thirds times the integral from 0 to 5 of, the antiderivative of the cosine of theta is the sine of theta. So that's going to be z times the sine of theta. And that's evaluated from wherever theta is equal to 0 up to wherever theta is equal to 2 pi. And here, that just gives us 0. Because notice the sine of 2 pi is 0, and the sine of 0 is also 0. So this will give us 8 thirds times the integral from 0 to 5 of 0 dz. Oh, well then that whole thing's just 0, isn't it? So in this case, the outward flux integral is 0. And although this may seem a bit anticlimactic, that's all there is to it. We take the divergence, and then we perform a triple integral over Q. Here, the only complication might be, well, sometimes integrals are a little rough, so you may have to change things to cylindrical coordinates. You may also need to use spherical coordinates depending on your object, or you may stay in rectangular coordinates, and it really does depend on the individual problem. But the complications usually come from the integrals. This setup, that really is all there is to it. So let's see one more. You'll find this is a reasonably short section, not because this material is particularly simple. We've taken an entire 5 chapters to get to this point, but mostly because, well, at this point, everything that needs to be said has been said, and it's just an application of everything we've learned going back this whole semester. So go ahead and give this a try. Take the, find the outward flux integral. Well, here, let me say find the outward flux. Integral over S of F dot N ds, where F is the vector field given by the vector xy, comma 4y, comma xz, and the surface S is x squared plus y squared plus z squared equals to 16. It's the sphere of radius 4. Okay? So give that a try. See if you can use the divergence theorem to turn this from a flux integral, from a surface integral, to a triple integral over the solid that's inside of this. And once you've transformed it, go ahead and perform the integral to get yourself an answer. My suggestion is, since you are doing things with a sphere, spherical coordinates is going to make things a little simpler. However, you can do it in rectangular. I wouldn't recommend it. All right, so go ahead and pause the video, give it a try, and once you're done, go ahead and unpause it, and we can finish this one off together. All right, so let's take a look here. We're going to write this using, well, first of all, let's find the divergence, right? The divergence of F is given by the partial with respect to x of the first component, plus the partial with respect to y of the second component, plus the partial with respect to z of the third component, which in our case, well, the derivative with respect to x of this one is y. The derivative with respect to y of this one is 4. And the derivative with respect to z of this one is x. Okay, so the divergence of f, I'm going to write this as x plus y plus 4. All right, so now I know by the divergence theorem that the flux integral of f through the surface S is going to be given by the triple integral over Q of the divergence of f dv, which for this particular example is the triple integral over Q of x plus y plus 4 dv. Okay. Now we know Q is the sphere of radius 4. Notice here the surface is the outer skin, whereas Q is all the stuff inside. So here I guess I should say that Q is x squared plus y squared plus z squared is less than or equal to 16. Here this is the hollow sphere, whereas here this is the stuff inside that sphere. So if we're going to take a triple integral over a sphere, we probably want to use spherical coordinates. So let's go ahead and write that as, using Fubini's theorem, we can write this as a triply iterated integral, and we're going to change its boundaries of integration from rectangular into spherical. All right. Of course, these change as well. Remember, when changing from rectangular to spherical, x is going to change to be rho sine of phi cosine of theta, y is going to change to be rho sine of phi sine of theta, like that. And since those are being added, well, that means these two are being added, plus a constant 4. And then dv, let me put these in brackets here in parentheses, dv, when you're changing into polar coordinates, into spherical coordinates, that's going to be d rho d phi d theta, but we have a Jacobian here, which for spherical coordinates is rho squared sine of phi, like that. So here that's your x, that's your y, that's still the number 4. All of this stuff is dv. And now we can go ahead and describe a sphere using spherical coordinates, which should be fairly simple because that's what they're meant for. Here, if you have a sphere of radius 4, well then rho is going to go from 0 to 4. From the pole all the way out to the outer skin where the radius of the sphere is 4. Phi, well, you want the upper and the lower half of the sphere. Remember how phi works? You're starting from the positive half of the z-axis. So here's phi is equal to 0. And then you're going to come down from there. So here I don't want to come down just to here because that would only give me the top half of the sphere. I want to come all the way down so that I'm facing in the opposite direction. So here that's phi equals to pi. 0, pi over 2, pi. So here phi is going to go from 0 to pi. Right. Since rho went from 0 to 4, I went from the origin out to the sphere of radius 4. Up to the out to the sphere of radius 4. Here I have phi from 0 to pi, and now theta tells me how far I'm going to rotate this. Well, if I take this flat half circle, if I rotate it all the way around once, that'll give me the full sphere. Okay, so then that means I want to go one full rotation. So theta, just like in polar coordinates, is going to go from 0 to 2 pi. So 0 to 4 gets me the right radius all the way from the pole up to the sphere of radius 4. Phi from 0 to pi gets me from the north pole down to the south pole, 0 to pi. And then 0 to 2 pi for theta spins this all the way around to give us a full sphere. Okay, so now we can go ahead and integrate this stuff. Let's see, it looks like I could distribute this stuff right here throughout these terms. I note that here I have a common factor of rho sine of phi. Here, I'm going to write it this way. I'm going to write this as, and it looks like it's going to take more than one page, but oh well. Integral from 0 to 2 pi of the integral from 0 to pi of the integral from 0 to 4 of. I'm going to go ahead and take these two and factor out rho sine of phi. I'm going to multiply it times this rho squared sine of phi to give me rho cubed sine squared of phi. Phi. And then when I factored these out, I was left with cosine of theta plus sine of theta. Notice that still says the same thing. That would be rho cubed sine of phi. Rho cubed sine squared of phi cosine of theta. Rho cubed sine squared of phi cosine of theta. Plus rho cubed sine squared of phi sine of theta. Yeah, rho cubed sine squared of phi sine of theta. Oh, but now I have to distribute that to this number 4. Okay, so I'll write that as 4 rho squared sine of phi d rho d phi d theta. Okay, so now, in spite of how unpleasant that looks, this is just a constant with respect to phi. So with respect to rho. So this is rho to the third times a constant, and the antiderivative will be rho to the fourth over 4 times the constant. And then over here, the antiderivative of this one will be 4 rho to the third over 3. And again, that's a constant with respect to rho. So I'll just leave it alone the way it was right there. That's going to be where rho goes from 0 up to 4. And then I still have two integrals to perform after that. So let me leave those there. I can now substitute in rho is equal to 0, which makes those both 0, so I don't care about that one. And if I substitute in rho is equal to 4, that's going to give me the integral from 0 to 2 pi of the integral from 0 to pi. 4 to the 4th divided by 4, that's 4 to the 3rd, which is 64, sine squared of phi times cosine of theta plus sine of theta. Plus 4 to the 3rd times 4 is 4 to the 4th, so that's 256 over 3 times the sine of phi, d phi d theta. Okay. So now the next thing I want to do, I want to integrate with respect to phi, which again, these are constant with respect to phi. I don't have to worry about that one. Oh, but that's an even power of sine of phi. So I'm going to have to use the power reduction formula. So here I can write this as, now remember, sine squared of phi is the same as 1 minus cosine of 2 phi divided by 2. Oh yeah, but that divided by 2, let me go ahead and put it with that 64. So here I'm going to write that as, this part right here is 1 minus cosine of 2 phi divided by 2. That's the power reduction formula. Oh yeah, but if I'm dividing by 2, let me go ahead and put it with this one and just turn that into a 32. I haven't integrated yet. That's just the power reduction formula. Power reduction. And here, this doesn't involve phi at all, so that just stays the way it is. Okay. But now if I'm integrating with respect to phi, well, I know how to integrate those. No, these are constants. 32 times cosine of theta plus sine of theta, that's just a number. That's a constant with respect to phi. So the only part I'm integrating is this part right here. So this is going to be the integral from 0 to 2 pi of, okay, the constants stay the way they are, so that's going to stay 32. And that's going to stay cosine of theta plus sine of theta. Here, the integral of 1 with respect to phi is going to be phi. And the integral of negative cosine of 2 phi is going to be negative sine of 2 phi. But then, because of the chain rule, I now have to divide by the derivative of this. So that's really going to be negative 1/2 sine of 2 phi. Over here, this one will be a little bit simpler. I don't have to worry about any power reduction formulas. That's just 256 over 3. The integral of sine of phi is negative cosine of phi. So I can write that as negative 256 over 3 cosine of phi. Here I'm going to evaluate from wherever phi is equal to 0 up to wherever phi is equal to, what did we have, pi? Like that. And so that becomes the integral from 0 to 2 pi of, all right, let's see here. If I plug in pi to these, that's going to give me 32 pi minus, let's see, 2 times pi is 2 pi. The sine of 2 pi is 0, and anything times 0 is 0. So that's just pi minus 0, times cosine of theta plus sine of theta. Again, I'm plugging in for phi. Theta's not been touched. And then right here, I plug in cosine of pi, and the cosine of pi is negative 1. So that's negative 1 times negative 256 over 3. So that's going to become plus 256 over 3. Okay. Now let me plug in 0 into all of these. If I plug in 0 here, that's going to be 0. And that's going to be 0. Okay, so that's 0. Right, that's 0. And then the sine of 0 is also 0. So this whole thing's 0. And these numbers times 0 are still going to give me 0. But over here, that's not 0. The cosine of 0 is 1. And that's going to be negative 256 over 3 times 1 is negative 256 over 3 d theta. Here I can clean that up as the integral from 0 to 2 pi of 32 times pi times that cosine of theta plus sine of theta. 32 pi times the cosine of theta plus sine of theta. Here, minus and minus makes that a plus, so that's going to become plus 256 plus another 256, that's going to be 512 over 3 d theta. All right, we're almost done here. Let's see here. That's going to be, I'm just rewriting this over here. That's going to be the integral from 0 to 2 pi of 32 pi cosine of theta plus 32 pi times the sine of theta plus 512 over 3 d theta. All right. So all I've done is I've rewritten that line. Here I've gone ahead and distributed the 32 pi. 32 pi times cosine of theta, 32 pi times sine of theta, and that just stayed on its own. Now I'm going to integrate that with respect to theta from 0 up to 2 pi. Okay, so let's go ahead and do that. With respect to theta, this is now a nice simple integral. Here that's going to be 32 pi times, well, let's see, we're going to integrate cosine of theta, which will give us sine of theta, plus 32 pi. If you integrate the sine of theta, you get negative the cosine of theta. And if you integrate 512 over 3, you're going to get 512 over 3 theta. And that's evaluated from wherever theta is equal to 0 to wherever theta is equal to 2 pi. All right, so now that's, let's see here. If I plug in 2 pi right here, that's going to give me 0. So that's going to be 0. If I plug in 2 pi right here, the cosine of 2 pi is 1. So that's going to be 0 minus 32 pi. Really 32 pi times 1, but the times 1 doesn't change anything. Plus, that's going to be 2 pi times 512. Well, we can write that as 1024 pi over 3. Multiply that there. And now minus, and now if I plug in 0, well, again, sine of 0 is 0, so that whole thing's gone. Cosine of 0 is 1, and 1 times negative 32 pi is negative 32 pi. And then here, if I plug in 0, that whole thing is also 0. So here I notice I have negative 32 pi minus a negative 32 pi. A number minus itself is going to be 0, so that goes away. So all that's left is our result, and that's going to be 1024 pi over 3. And so by the divergence theorem, by Gauss's theorem, that means that our outward flux integral of this vector field over this sphere is given by that amount. Since that's a positive, that means that it's there's a net flow outwards. For every unit of time, that's how much stuff, that's how much of your fluid is flowing out from within inside that sphere. And that is it for the section. As an assignment, you may wish to try the following problems for 15.7. Number 1, that's a conceptual question. It doesn't ask you to do any computation. Rather, it asks you something about a type of computation or types of computations. 9 through 19 odd, those are very mechanical. Let's see if you know how to set up a flux integral using the divergence theorem, and then integrate. All the integrals are reasonably nice, nothing terrible, although there's a few of them that you may wish to convert into other coordinate systems. And then try problem number 25. For number 25, it is another sort of conceptual question. It's almost like a proof, but not quite, because you don't quite go into that much detail. There is going to be a temptation to want to make a computation to number 25. Don't do that. That's going to be a lot of effort, and it's not really going to get you anywhere. For number 25, don't think computationally. Think conceptually. In particular, there's going to be a theorem going back to chapter 15.1. I won't tell you which one it is, but there's a theorem in 15.1 that will make doing this one a lot more manageable. All right, so conceptual, and these are just nice applications of our theorem here, our divergence theorem. So that is it for the section. If anybody has any questions, comments, or problems, please make a note of those. Contact me. Go ahead and reach out to me, and I'll help you with what I can. All right? And I hope everyone has a nice day.